Well, good afternoon, everybody, and welcome to the third and final webinar today from Smart Vision Europe. In this webinar, we're going to be talking about interpreting correct interpretation of significance tests, what we call tests of significance or statistical tests. My name's Jarlath Quinn. I'm an analytics consultant. I'm joined online today by my colleague Rachel. Rachel will be just making sure everybody's logged in correctly and dealing with any issues with regard to you joining the webinar. If you haven't joined any of these before, I know that some of you have joined from earlier sessions that we ran today. The sessions are, like all of our sessions, recorded, so you'll be able to listen to them again afterwards. And this is a session which does have a lot of slides in it because we're talking about quite abstract concepts and we're trying to put a lot of context around anything that we demonstrate. So that's going to be quite important. As a result of that, we'll email a link out to you, which will allow you to download the PDF of the slide material, which will act as an aid memoir after the session's ended. If you think it's really useful for other colleagues who were unable to attend today, and you can get enough of them together, it may be possible for us to arrange a rerun of the session on a private basis. The best thing to do is just send us an email, and we'll see if we can do that. Now, with regard to asking questions, all the lines are muted. I may ask you to use the chat panel. Rachel will be checking those as we're going along, but every now and then I'll see if I can remember to just interrupt myself and check and see if there are any questions that have come up. If you don't know who Smart Vision are, we are a partner to IBM. In fact, we're a gold accredited partner to IBM, as well as a company called Predictive Solutions and DataRobot. And we specialize in statistics and data science, machine learning, advanced analytics, and AI type technologies. We also work with open source technologies as well as IBM technologies and Predictive Solutions and DataRobot. We work with R and Python, Spark, which are widely used within the analytical realm. We're a relatively small organization, but we are a team that has very deep experience stretching back over decades of working in the advanced analytical technology industry, i.e. software, what we used to call software. The common denominator being that we've all worked for SPSS Incorporated. We're all members of the senior SPSS UK team at one point in the past, and our experience stretches back to the 1990s. I've also worked for IBM as a consultant and also for SAS Institute as a consultant. And that basically means that we've all got pretty deep experience of applying analytics across many different sectors, many different applications over the past 30 years. Now, the subject of today's webinar, this final webinar, is about significance testing. It's a popular webinar. We get a lot of people joining it on a regular basis every time we run it. And I guess that is testament to the fact that this is still an area of vagueness and confusion to people, even when they've been exposed or been taught something about statistics in the past. And we really wish to demystify that and to put some sort of clarity around what a significance test is, where it comes from, and how you make a correct sense of it. And our agenda, therefore, looks at how the term significance testing came about, how it fits into the realm of what's called inferential statistics, how we actually interpret the numbers that significance tests punch out, particularly the p-values. And then we'll look at three examples. We'll look at calculating a chi-square test, which is used when you're analyzing the relationship between groups of categorical or category variables. And we're going to look at correlations, which is a way for us to illustrate how to measure the strength of a relationship, a linear relationship, usually between continuous variables or sometimes ordinal variables. And the last thing we're going to look at is interpreting confidence intervals correctly. We don't really have time to go into ANOVAs and t-tests, stuff like that, but confidence intervals are a good sort of gateway topic to that. And the other reason we're calling that out is because they're so often misinterpreted, and we wanted to give people the correct language and explain to them why they're commonly misinterpreted, and show how they come about and how they help us make inferences, even if they're not technically tests of significance. So let's start with some historical basis here. First of all, the term significance is a troublesome term to most people working within the statistical realm. They don't like the term significance. I certainly don't like the term significance. People talking about things being statistically significant as if that meant something was important, and that's not really the case. The person who's responsible for that is Ronald Fisher. And R.A. Fisher is really the father of inferential statistics. He was a British statistician. Had quite the reputation for being quite a character and not necessarily in the most positive way. But he's the person that really came up with a lot of the terminology and the thinking of what we would call the frequentist tradition. So he introduces the phrase tests of significance in a book in 1925 called Statistical Methods for Research Workers. Now, unfortunately, that's not a great term to use because saying that something is statistically significant is likely to be misunderstood because significance often means notable or significant, really, really important. And in this case, significance does not mean necessarily that something is notable. In fact, sometimes it doesn't even mean it's necessarily reliable. And even the term test is slightly problematic. When we talk about tests, somebody says, I tested it and found that, there was nothing there, or, so we tested somebody for an illness and found that they were positive for it. In this case, statistics aren't really these inferential statistics, these tests of significance aren't tests in the sense that one would assume they have the same degree of reliability, perhaps, that other tests have. Um, if we were coming up with a literal phrase to describe a significance test, a literal phrase, which I don't expect anybody to start adopting anytime soon, would be a probability of evidence estimate. And that's really what they do. They tell you the probability of some evidence being reliable, being true, and it's an estimate rather than a test. So when we start to think of it in these terms, this is about probability of evidence, probability of data being true, and that it is an estimate of that probability. Then we start to have some more respect for the limitations of tests of significance. Now, in fact, there are a bunch of people, not just Ronald Fisher, who really form a lot of the core concepts around what we call inferential statistics, sort of classic statistics, the stuff that we're taught in university in Stats 101, if you like. And all these terms that we're introduced to, things like null hypothesis and confidence intervals and significance and chi-square, the names of the tests, F tests. F comes from Fisher, Ronald Fisher. Pearson's correlation, maximum likelihood, principal component analysis, all this sort of stuff, alpha levels. It all comes down to a relatively small group of people. One of whom is Ronald Fisher. The other was his rival, if you like, and his contemporary was Karl Pearson. So a lot of statistics named after Karl Pearson. Then there is Egon Pearson's, Karl Pearson's son, working in the 1950s with his co-worker Jerzy Neyman. And it's fair to say that these people didn't necessarily all agree with how statistical analysis should occur or how it should be interpreted. And as a result of that, statistics in this tradition is something of a kind of a smorgasbord, really. It's not you often hear statisticians say it's not an exact science. It's not like physics. It's not like everything has to link together. These are a bunch of different tools that overlap with one another to a certain degree, which measure different aspects of variation and try to make judgments about what's happening in the real world. So this is known as the frequentist tradition. The reason why we point this out is because there is another statistical tradition, and one which has become much more popular in recent years, and that is the Bayesian tradition, which takes a completely different approach. It's almost as if the frequentist tradition never existed. But we're talking about frequentist tradition and certainly tests of significance. When you're talking about significance tests, you're really talking about frequentist statistics. So in order to talk about significance tests or tests of significance, we have to broach the subject of inferential statistics and what we mean by inferential statistics. So if we're just taking an average, we're just calculating an average of some data or a median or the percentage of cases that fall within a certain group, these are known as descriptive statistics because we're simply restricting our judgment to that data set. We're not saying anything about the world or more generally the population from which that data set came. We're just describing what's in the data set. As soon as we start to use that data set to make judgments and to make claims about how it reflects the population that it came from, we're into the realm of inferential statistics. And inferential statistics is thus called because every data set that we have is effectively a sample, even if it's just a sample in time. The world is changing all the time. So a statistic is a value which is a characteristic of a sample of data, whether that be a census or whether that be a survey or whether that be an experiment between left-handed and right-handed people, or whether it be sales figures for a company over a period of years, something like that. It's still a sample, and any numbers that we draw from that are referred to as statistics, technically speaking, because statistics refer to samples. Now, on the other side of that is this theoretical world from which the sample is drawn. This is known as the population. And the equivalent of a statistic in a population you can think of as a parameter. So a parameter is a characteristic of a population. If I estimated the mean, I don't know, the mean age, let's say, of people in the UK at this exact moment in time, I might go and take a sample of 1,000 people and hope it's random enough and it's not biased in any way, and calculate the average age and say, there you go, there's a statistic that shows the average age is, I don't know, 35.6 or something like that. The actual average age, which is at that exact point, or which is changing all the time, of course. And if we take it to like 16 decimal places, the number would be changing on a regular basis, on an hourly basis, of course, because people get being born and dying all the time. The parameter, that would be a parameter, that number that's actually out there in the population is a theoretical number in many ways, is a parameter. And a characteristic of inferential statistics, and a characteristic of frequentist statistics, more importantly, is that the parameter is an actual number. It's just an unknown number. It's out there. And in the Bayesian world, it's more of a random variable. It's a bit more fuzzy. But anyway, so that's the idea behind it. Statistics come from samples, and parameters are part or characteristics of the population from which the samples are drawn. So how do we infer the parameter of a value from a sample statistic? Well, obviously, one of the ways in which we do it is we try to take a representative sample. That's a hard thing to do. And we try to take a large enough sample, and that's a costly thing to do and requires resources. But even when we do that, there's no guarantee that we've correctly inferred the parameter value of the population. There's no guarantee it's exactly the same. And this is especially true when we're trying to compare groups. So, for example, we find that when we draw repeated samples from the same population, we produce slightly different statistics. Even if I was sampling water from the Indian Ocean and trying to calculate the salinity of the Indian Ocean, and if I was doing it to enough decimal places, and sailing a boat around and taking different samples, it shouldn't surprise me at all that these numbers will vary somewhat. They vary from one another, and that variation is critical, because that's what we're interested in. We're interested in variation. In fact, one could say that statistics is the science of variation. It's how things vary from one another, and we are interested in separating the world of non-random variation from the world of random variation, saying something, whether or not differences are due to pure random chance, or whether or not they're due to the fact that these differences, or these values that we're calculating, these statistics, are simply reflections, mirrors, if you like, of what's happening in the population. So if we were to draw three samples, let's say, from a large population, we wanted to calculate the mean ages of the men and women in the samples, we might well find, as you would expect, that the mean ages might vary somewhat. And here we can see the mean ages are varying, to a reasonable degree here. 34 for the men and 32 for the women, or 33 for the men, 30 for the women, or 31 for the men, 32 for the women. So they vary from one another, and that's important, because what we're interested in is whether or not these differences that we're observing in our given sample. Let's say we take one of these samples, we don't get the chance to take three. We're asking whether or not those differences actually exist in the population. And in many ways, what we're asking is if they don't exist in the population, perhaps the mean ages are in fact exactly the same. Maybe they're just both age 32 or something like that. And that is what we're trying to ascertain when we do a test of significance, when we're comparing two means, for example. Is it possible that they're actually just the same in the population and the differences that we're observing are simply artifacts of the fact that they are samples and the sample's not the same as population? So where does significance come from? Where does the significance come from? Well, the significance does not mean noteworthy. And these tests that help us figure out whether or not it's possible that the means are in fact identical in the population simply indicate that the evidence does not support the assumption. So we do a test of significance, it might tell us, it might give us a number that says the evidence does not support the assumption that there's no difference between certain groups in the population. Now, rather annoyingly, the way in which this evidence is shown to us, even within the same software package, whether it be Minitab or Statistica, but especially within the SPSS, you find that they're labeled in different ways. So they're not always labeled P for probability. Sometimes they're labeled SIG for significance. Sometimes they're labeled prob. Sometimes they're giving longer labels like asymptotic significance, which means kind of estimated significance, if you like. And there'll always be a number associated with them. So the good thing here is at least the number is interpreted exactly the same way, even if the label is different, but the number is interpreted exactly the same way. And the number can always be converted to percentage. So a sig value of 0.001 indicates 0.1%. You basically multiply it by 100 in your head to get used to doing this. A value of 0.172 multiplied by 100 comes out to 17.2%. And a value of 000 doesn't mean that it's the zero probability. It just means that the number is too small to display. And the value of 0.0344 here means 3.4% or roughly 3% if you're rounding downwards. So this is how we interpret the numbers, and we bear in mind that these numbers may have different labels, but they're interpreted the same way. This is how we convert them into numbers like percentages that make sense for us. In fact, these days, SPSS usually just labels them as, greater. If the number is really small, it'll just say it's less than 0.001 or something like that, or less than 0.05. So it won't necessarily automatically label and show you the exact number, though you can get it to do that, and it will show it to 16 decimal places if you want to see the exact probability or p-value that's produced. So returning to our example here, if we assume there is no difference or no relationship between the groups, we assume there's nothing going on and that everything that we're seeing, the differences we're seeing are actually just driven by the fact that it's sample rather than the population. If we were comparing two averages and we calculated a t-test for a sample from a population, and we calculated p-values for those t-tests, and what those p-values are simply telling us is that, let's assume this is a sample of, I don't know, 100 males and 100 females. It's saying that, based upon that information and based upon the t-test we're doing, we would see a difference as big as this 11% of the time, even if there's no difference between the two groups, between the males and females. We'd actually see that difference 11% of the time. Whereas if the value was equal to 0.04, it would say, we would see a difference as big as this, 4% of the time. And if it was 0.33, it says we would see a difference as big as this 33% of the time. However big that difference is. So, it might be the difference is tiny. So we're using the term big in inverted commas here. So that's what it's doing. It's telling us how often you would see that result in a universe, if you like, where there's no difference between the two groups. In the same sense that, if you knew for absolute certain that the coin you had in your hand was a fair coin, there was no bias in it, and you flipped it 100 times and it came up 75 times heads and 25 times tails, and you said, wow, how often would I see a result as extreme as that, when I know that this coin is fair? This is the context within which we are interpreting the p-value. Okay. So significance tests are directly related to this concept of hypotheses or hypothesis testing, and we need to talk about that. If you are investigating a relationship with statistics, it's usually because you're curious to see if there is a pattern or difference between groups. In other words, that means you have a hypothesis. Example, I think that there's a difference between the average age of men and women in my population. That is usually labeled the alternative hypothesis, or H1 for short. That's basically the statement that reflects your hunch, your idea, your notion. I wonder if there's actually a difference here. But in reality, of course, you're testing to see if your data supports the idea that there is no difference between the average ages of men and women in the population. And this is called the null hypothesis, H0 for short. It assumes you're living in a universe where there's no difference. It assumes you're living in a universe where cancer is not caused by smoking. And you're going to do a test and you're saying, wow, look at that. There's a big difference here between smokers and non-smokers in terms of the cancer rate, assuming that cancer is not caused by smoking. How often would I see a difference as big as that? The relevant test then calculates a probability that indicates that if the null hypothesis is true, or in a universe, if you like, where the null hypothesis is true, how often would we get a result as extreme as the one we've observed? So that means that we have to say something about this null hypothesis. We have to say, well, can we support it? And when we do that, we're saying, well, how small or large does this p-value have to be before we decide that the data doesn't provide enough evidence to support this null hypothesis, where we say that, this coin can't be true, this coin can't be fair, or this relationship is unlikely to simply be a random effect. It almost certainly we can't support the notion that we are living in a universe, if you like, where cancer isn't caused by smoking. That's the thing. So we have to choose. We have to choose a threshold. What threshold should we choose? I mean, you could choose 32%. You could say if it's less than 32% chance that null hypothesis is true, I'm going to say, I'm going to say there's not enough evidence to support it. Or maybe you have to be really strict and say, okay, it has to be less than 0.0001%, which would be a very small probability value. And if it's less than that, then I'm going to say, right, there isn't enough evidence to support the null hypothesis. Now, clearly, you have to choose some level. You have to choose a threshold. And that threshold is therefore always going to be arbitrary. It's going to be a line in the sand. It's going to be a convention. And that convention, that threshold, is called the alpha level. And it is indeed fairly arbitrary. R.A. Fisher said, I don't know, maybe 1 in 20, maybe about 5%, which would be p equals 0.05. In fact, he said there may be occasions when it has to be 1 in 100, or, or 1 in 50 or something like that, maybe 1 in 200. But he said, generally speaking, he thought that 1 in 20 seems to be a reasonable number, because it kind of roughly relates to 2 standard deviations above the mean. On this basis, if the probability is less than p equals 0.5, we would reject the null hypothesis, if we're assuming that's our alpha level, on the basis that there is insufficient evidence to support it. So now at this point, we have to talk about accepting or rejecting the null hypothesis and make sure that we've got ourselves straight in this area. The alternative hypothesis is there only for reference only. We never accept or reject it based on our analysis. You might refer to it in the report you're writing, but frequentist significance tests have nothing to say about the alternative hypothesis. They only refer to the null hypothesis. And in fact, they only refer to the null hypothesis in a really, really one-dimensional way. You never even accept the null hypothesis. The most you can do is either reject it or not reject it. So that's what we do with the null hypothesis. We either reject it, we don't reject it. We don't accept it, and we don't say anything about the alternative hypothesis. Some analysts would argue this is a real limitation of classical frequentist statistics. And a completely alternative approach to hypothesis testing can be found in Bayesian statistics, where we compare how much evidence there is for the null hypothesis versus the alternative hypothesis. So in Bayesian statistics, it does say something about the alternative hypothesis. In fact, it shows the ratio of evidence for the null hypothesis to ratio of evidence to the alternative hypothesis. And for more information about that, you can check a little video series that we've done on that and link to that. But in the world of significance testing, and then therefore in the world of frequentist, all we do with a p-value is we either reject a null hypothesis or we don't reject it. And by not rejecting it doesn't mean that we accept it. We just don't reject it. Contrary to a lot of statistical teaching, the p-value does not indicate that the probability that null hypothesis is true. and it does not indicate the probability that the data were produced by random chance. What p-values can do is indicate how compatible or incompatible our data are with the null hypothesis. And in other words, how compatible and incompatible our results are with the null hypothesis when we analyze it. Now, that might sound like semantics, but it's not. For a start, the probability of x given y is not the same as the probability of y given x. They're two different things. So, for example, if you say, what's the probability of somebody having a full driving license given that they're age 17 or over? So you pick somebody random from the population. You say, this person's aged, I don't know, 28 or something like that. You say, what's the chance that they've got a driving license? Because they might not have a driving license. That's not the same thing as saying, what's the probability of somebody being age 17 or over, given that they have a full driving license? If they've got a full driving license, at least in the UK, they have to be age 17 or over. So it's it's a 100% chance, technically speaking, on that. The two things are not the same. So when we're calculating our null hypothesis, we are saying the probability of the null hypothesis is being true given the evidence. It's not the same as the probability of getting that evidence, assuming the null hypothesis is true. That's what we're doing. We're saying the probability, how often, what's the chances of getting that evidence, of getting that result in a world where the null hypothesis is true? And that's why it's important to get the language correct around this. So the null hypothesis is pretty important in these tests of significance. And when we look at all the different types of tests that are available in the package like SPSS, there's over 200 tests of significance. It turns out the way in which one of the ways in which we can make sense of these tests is if we know what the null hypothesis is that's associated with each test. So to correctly interpret any significance test, you really have to know the null hypothesis associated with it. And it turns out, for example, for a chi-square test, the null hypothesis is that the two variables are independent of one another. They are not related. And your p-value either gives you enough evidence to reject that or not reject it. If it's less than p equals 0.5, the convention is that you reject it. And if it's greater than p equals 0.5, the convention is that you would not reject it. A t-test or an f-test, however, doesn't look at whether two variables are independent of one another. It actually focuses on averages, on means, and it's testing whether or not the two means are in fact just the same in the population. The difference you're observing is simply a reflection of your sample. It's nothing to do with it's random chance. It's not actually mirroring the population exactly. Pearson's correlation value. Here, the null hypothesis is that the correlation value is actually 0 in the population. It's not, the null hypothesis is not that there's a weak relationship or there's not much of a correlation. The null hypothesis is that there's no correlation, no linear relationship in the data. And that's important. There are other tests which are used, almost a test of tests, that test whether or not you have equals spread in two groups. Sometimes those tests are used to test whether or not you can do a t-test or an f-test. That's called Levene's test of equality of variance. That would be an example of that. And here it's testing the null hypothesis that they've got the same spread in the population, that the same standard deviation, if you like, in the population, in the same way that in the t-test is testing a null hypothesis, the averages are the same. Or a null hypothesis for a KS-Lilliefors test is that the data are normally distributed in the population. This confuses the hell out of students, because they think that getting a p-value of less than 0.05 means that you find an effect. You're not don't think of it in terms of finding an effect. It is whether or not the null hypothesis can be supported. That's what it is. So if the KS-Lilliefors test null hypothesis is that the data are normally distributed, your data is normally distributed, then you would only say that the data is that can't be substantiated, that you can't support that if the p-value is less than 0.05. And if the p-value was greater than 0.05, greater than or equal to it, you'd say there's not enough evidence to reject the null hypothesis that the data is normally distributed. And you would therefore say, on balance, I'm going to assume that this data is normally distributed because I haven't got enough evidence to reject it. That's fair. So this is why the understanding what each test's null hypothesis is associated with it helps us make sense of the p-value. What is it that we're rejecting when we reject a null hypothesis when we find a value which is less than our alpha level? And it might not, bear in mind, it might not be p equals 0.5, it might be p equals 0.1. Some people work at a 1% level, depending on the field of research that they work within. So let's talk about our first example here. We've got crosstabs and chi-square tests. Let's talk about crosstabs. So crosstabs, as you're probably aware, are just tables, and they're a way for us to examine the relationship between category fields. So crosstabs are really associated with category fields. Here we're looking at the relationship between gender, people, employees' gender, and their employment category. Okay. And if I run that crosstab, it's just going to give me a series of counts. It's going to say, look, there's 206 clerical workers in the female group. There's 157 male workers in the clerical group. There's no female custodial workers. There's 27 male custodial workers. There's only 10 female managers, but there's 74 male managers. And it's hard to interpret that, isn't it? Because the group sizes are different. Look, there's 258 males and 216 females. So what we tend to do is we tend to add in percentages. And we say 95% of the females are clerical workers compared to only 60.9% of the males. And this is how we interpret it. At this point, we might start to say, what's the probability that in fact your employment category is your employment category is not related to your gender, that your gender is no way related to your employment category. It's not that one is dependent on the other. It's just that they're both completely independent of one another. Or is there some sort of, does one tend to affect the other in some way? Of course, employment category is not going to affect your gender. We know that. We know that gender may affect your employment category. And therefore, we may do a statistical test associated with that. Now, if I just jump out and just show you how you do this. So I go to Analyze here and down to Descriptive Statistics and Crosstabs. It should say rows here. I think this is something they haven't labeled correctly yet in version 30 of SPSS, but I think they're going to change it soon. And if you look back here in this example I have in my PowerPoint slide deck, you can see females are in the rows, and genders in the rows, employment category is in the columns. So I come back to this, so it's put gender in the rows, employment category in the columns, and we'll go to cells and ask for row percentages at that point. It reproduces the table that we saw earlier on. Okay, so we get the same, should be getting pretty much the same table. Okay. What happens if we want to do a chi-square test here to see if these two variables are independent of one another? Well, it turns out there is this sort of really special value you can get called an expected count. Let's just look at this. If I go back here, I'll rerun the crosstab. I'm going to switch off the row percentages so I see the observed count. But you can see under that, we've got an expected count. Click continue and OK. Now we're getting two counts. We're getting a value of 207 here and a value of 166.3 here. You can see the slightly different. The data is slightly different, but it's roughly the same because I think the data set's somewhat different from one to the next. But anyway, the point is, where's this expected count coming from and what does it refer to? Well, the expected count is one which adjusts for the fact that, you got less females than males. And it shows how many females you would expect to get if there wasn't a bias towards females being clerical workers, if it was equally distributed. And it's worked out very simply. You simply take, for each cell, you take the row total for that cell, which is 216. And for each column, the column total for that cell, 363. And you divide it by the grand total, which is 474. And that gets you the expected count. So there it is for the expected count. And you do that for each cell. Gives you the expected count. This is exactly the same as flipping a coin 100 times, having it come up 75 times heads and 25 times tails, and saying, what would my expected count be? Well, my expected count would be 50-50, wouldn't it? Because I'm adjusting for the number of possible outcomes. So now we've got a difference between what we expected to get and what we actually got. And the expected count here, if we look at the differences between the observed and expected count, these are called residuals. And they simply show you're getting 40 more females in the clerical group than you expected. You're getting 40.6 fewer males in the clerical group than you expected. You're getting 28 more males in the manager group than you expected, assuming that gender didn't make any difference to your employment category. And you're getting 28.3 less females in the manager group than you expected. They expected you to get about 38 females in there, but in fact you only get 10. Now, if we wanted to add those in, that's really simple. You just go to crosstabs and you go to sales again, and look, you can ask for residuals. Unstandardized, this means raw residuals, and it gives you the residuals. It shows you the differences between the observed and the expected. So what happens if we add these all up? Why would we add them up? Well, obviously, we add them all up, then the bigger that number is, the bigger the deviation in the entire table between the observed and expected. The bigger the bias there is in the table, the further away it is from what we from a situation where gender is in no way related to your employment category. But the problem is if we add them all up, if I add 40.6 to minus 40.6, obviously we're going to get zero. It's going to cancel each other out. So what it does is it squares the residuals. That's what statisticians do. We tend to square them. And that's why it's called chi-squared or chi-square. So we square the residuals. And when we add up all of the squared values, that we're not, it's a little bit more complex than that because we look at the ratio of the squared values to the expected frequency and so forth. But effectively, what we're doing is we're adding up these squared residuals, and the larger that number, the less likely it is that the variables are unrelated to each other in the population. This value is the Pearson chi-square statistic, which in turn allows us to calculate a probability. Here, the probability is labeled asymptotic significance two-sided. Two-sided means we don't assume that one affects the other. That we don't expect to get more females managers than male managers. We don't expect to get more male managers than female managers. The direction of the bias could go in either direction. Just means that way. And that gives us a p-value of Pearson's chi-square. Pearson named after Carl Pearson. And the null hypothesis associated with the Pearson chi-square test, of course, as we remember, is that the variables are unrelated to each other. So a probability of less than 0.05 indicates that differences as large as the one observed would only occur less than 1 in 20 times when this null hypothesis is true, and this leads us to reject the null hypothesis. So if I wanted to add in my test here, I'm going to go back to sales. I'm going to switch off the expected and observed frequencies. I'm going to switch on the percentages again. And I'm going to ask for statistics. I'm going to ask for a chi-square test. There we go, we're adding in. See, there's lots of other tests of significance here. And in fact, it doesn't just give me one test, it gives me two tests, it gives me a likelihood ratio, a slightly more sophisticated version of it. And here in the modern, more recent versions of SPSS, it just says that, look, the significance value is actually less than 0.001. So it's not even less than 0.05. It's not even less than 0.01, which is 1%. It's actually less than 0.001, which is less than 1 in 1,000. And you can double click on these and see the full number, which is 18 decimal places back. It's a very small number. It's saying there's a very big bias here. That would lead us to reject the null hypothesis that these two variables are unrelated to each other. And we wanted to report this result, we'd say the chi-square test indicates that the probability of obtaining a value as extreme as the one observed is less than 0.01. In this case, in fact, less than 0.001, assuming the variables gender and employment category are unrelated. Given this result, there appears to be insufficient evidence to support the null hypothesis, and it is therefore rejected. So a chi-square test is driven by the difference between the observed count and the expected count. And when we add up all those differences, the differences are called the residuals, and we square all the differences so that they don't sum to zero, it's going to give us a number which is a chi-square value, something similar to that. And that relates to a point on a curve. And we would, back in the day when I actually had to calculate this in school, what we'd do is we would look up the chi-square value and we would adjust for the degrees of freedom. Were these two values in a booklet of chi-square tests, chi-square values, it would give us an associated probability value. Degrees of freedom actually relates to the number of rows and columns in the data set. It's actually calculated as the number of rows minus 1 multiplied by the number of columns minus 1. We have 3 columns, minus 1's 2. We have 2 rows, minus 1's 1. 1 multiplied by 2 gives you 2 degrees of freedom. In other words, it's just an adjustment for how big the table is, because obviously if you've got a really big table and you're comparing lots of groups, there's a chance there that you could get quite a big difference between the observed and the expected. So that's a perfect example there of how we would interpret a significance test and a p-value where we're comparing the relationship between category fields against a null hypothesis, where we're saying the null hypothesis states that the two variables, the two factors, if you like, are completely unrelated to each other. If I went back to this and said, okay, I want to run this again, and I could try and find something which isn't related to each other, like minority classification against gender, and do that. It's actually leads me to not reject the null hypothesis. It's a 2 by 2 test. When you got 2 by 2, it gets 1 degree of freedom. It actually gives you an extra significance test called Fisher's exact test. It doesn't matter really, because you can see that all of these values are greater than 0.05. We would not reject the null hypothesis. We would not reject the null hypothesis that gender is unrelated to minority classification in this case. Yeah, so we would not reject it because the differences are not sufficiently large enough for us to say that that would occur less than 5% on occasions. This leads us to our second example here, which is correlation coefficients. And we're really interested in when something is significant, but not that significant, not significant in the sense that it's notable. It's a great example of how just because something's statistically significant doesn't mean it's notable. Here is a scatter plot. And the scatter plot shows a strong linear relationship between the employees' salaries and their beginning salaries, as you would expect. Employees who start on a high salary tends to mean that their current salary is also high as it grows over time. You wouldn't expect that people who start on a high salary end up with a current salary which is low. So there's a linear relationship between the two. And in fact, we can draw scatter plots of lots of different relationships. Here is a series of scatter plots. We're looking at the relationship between vehicles or cars. Each of these values here is a car. Each of these is an automobile. And this scatter plot here shows the relationship between the vehicle weight and the horsepower. In fact, I do a little webinar which is recorded specifically in correlations and goes in more depth. So if you want to learn more about that, you might see a recording of that on YouTube or on our website. Here is another scatter plot. We're looking at miles per gallon against time to accelerate from 0 to 60. Note that the relationship is weaker. This one's forming a straighter line. This one's a bit more for cloud points, but it is generally going upwards. And this one's going in the opposite direction. This is a minus relationship. Look, this is a minus number. As horsepower increases, time to accelerate from 0 to 60, it takes you longer to do that. It takes you longer to accelerate from 0 to 60. So if you have great horsepower, it doesn't take you very long to accelerate. This is a negative relationship. This is the relationship you get with reflex reaction time and alcohol intake. You get a negative relationship. And it turns out the correlation value that is calculated with this tells you the strength of this relationship. The closer it is to 1, +1 or -1, the stronger the correlation. In fact, if we were to correlate horsepower against horsepower, it would be a correlation of 1. It would be exactly 1 because it would be a perfect relationship. This is known as Pearson's R, named after Karl Pearson, of course. If there's no correlation, if there's no real linear relationship, it just looks like a random series of points, then the value gets very close to 0. So if it's very close to 0, it means there's no relationship. Here we have the relationship between mileage and miles per gallon. Mileage is simply a relationship. It just simply reflects how old the car is. And why should an old car have fewer miles per gallon versus a newer car? It doesn't really affect it that much. So the two things are unrelated. And the last example here is just to show that correlations can't see curvy linear relationships. They can only see straight line relationships. They can't see curves. So here we're seeing a negative relationship between miles per gallon squared and engine relationship. And even though it's a sort of a bendy banana-shaped relationship, the correlation is based on the straight line. And it's a relatively strong correlation, nevertheless. It's more than 0.3 is kind of the point at which people start paying attention to correlations. It's -0.6, it's a negative correlation. It doesn't mean that one is dependent on the other. It's just saying that, as one goes up, the other goes down. That's all it's saying. Okay. So if we were to get SPSS to calculate correlation values for it, it's very easy to do that. You simply go to analyze and you go down to correlate and you go to bivariate here. And you pick up, I'm going to look at education level against current salary and months since hire and previous experience. I'm going to look at age. I'm going to chuck them all in together. And I'm going to ask it to show only the lower triangle of the correlation matrix and not to show the diagonal. If I click OK, the reason I'm doing that is because it's easier to interpret. And I can actually double click on it and I can pivot this so I can hide some of the values because it's a bit confusing to begin with. There's a lot of statistics in there. So I'm just looking at the correlation value. Here are the correlation values themselves, okay? Let's jump back to the slides and look at them. I've highlighted some of the stronger correlations here. You can see, look, this was really strong. Relationship between beginning salary and current salary, very close to 1 at 0.88. There's a strong relationship between education level and people's current salary. Of course there is. The more years of education you have, the higher your current salary. And the more years of education you have, the higher your beginning salary. Look, here's a weak relationship. People's experience in months versus months since hire. It's very close to 0. Why should, if you've got a lot of experience, prior to joining the job, that doesn't affect how many months you've been in the job. So we're going to get weaker relationship. Here's interesting. Previous experience in months is actually negatively related to education level and years. So that's because the older people who were often custodial workers in this bank that this data set was taken from tended to have fewer years of education. So previous experience, if they're older, they tend to have more previous experience. So we get this negative relationship, okay? But which ones are statistically significant? Well, actually, if we look at the current output in SPSS, it actually flags those which are statistically significant at the 0.01 level, the 1% level with 2 stars, and those which are statistically significant at the 0.05 level with 1 star. Okay. So you can get ones which are statistically significant and have 1 star. Here's one here. There's 1 star. That's statistically significant at the 5% level. Okay. Let's jump back and look at that again. Turns out I can actually add in the significance values here and I can see them. But we have to remember this. Remember this, that the null hypothesis for Pearson's correlation is that the value is actually 0 in the population, no linear relationship. So when we add in the significance values, what do we find? We find that when we look at previous experience in months, it's statistically significant. Same value I pointed out there, 0.034. But look at the correlation. It's quite close to 0. It's minus 0.097. But it's statistically significant. So what does this teach us? We're being taught something here. What we're being taught is this statistically significant? Yes, because the probability of getting a result as extreme, in inverted commas, as minus 0.097, assuming there is no relationship between the two variables in the population, is still only 3.4%. Does that mean it is notable or worth reporting? No, not particularly. But then that's not what the null hypothesis for Pearson's correlation value is directed at. It only states that there is no linear relationship there at all in the population. So it says, yes, it's statistically significant because we're rejecting the null hypothesis that this correlation is in fact 0 in the population. But we're not saying that it's a strong correlation. We're saying it's actually very weak. It's a very weak correlation between people's previous experience in months and their current salary. Would we note that in the report? I don't think you probably would. So it's a classic example of when something is significant statistically, but it's not significant in the sense that we would say it was notable or worth pointing out. And that's why knowing what the null hypothesis is that you're testing with a particular procedure you're running is so important. And you'll get people saying, I've got a significant result here of my correlation. Yeah, you might have, but it's so weak. It's barely worth pointing out. Okay, the last example we're going to look at is confidence intervals. We're going to run this as a fun example. This is where we're comparing means, if you like, comparing averages. I didn't want to get into the t-test because that's a bit involved. But as we know, different samples from the same population vary. If you repeat a survey or a project, you won't get exactly the same results. You calculate a statistic, and the results will vary from one sample to the next. Of course, we've talked about this. No statistical calculation can tell you what the actual value is of a population parameter. It can't tell you what it is. It's theoretical in nature. And we don't normally have the luxury of repeating samples over and over again. You usually have one go at it. But we can estimate a range of values that it is likely to lie within. And I'm really underlining the word a here, a range of values. And we can do this by requesting what are called confidence intervals. Confidence intervals are shown graphically as error bars. They look like the little TIE fighters on the side here, where the dot in the center refers to the mean, normally, confidence intervals for the mean. And the upper and lower bars refer to the intervals. These are the error bars themselves. Now, the explore procedure in SPSS produces lots of summary measures. And here it says that the mean age for the people in the sample was 34.74, and the confidence intervals were 33.67 versus 35.8. So if I just show you how to get that, you go here to Analyze Descriptive Statistics, Explore. I pick up age and put that in there. It's called the dependent. You could actually break it up by gender. I'm going to pick it up for gender here. I tend to switch off the plots. I'm not really that interested in them that much. But the statistics will always give you, it gives you a bunch of stats. It gives you loads of stats out there, but it gives me the confidence intervals for male and female. Look, there's the confidence intervals for females, 36.27 versus for males, 35.99. And I could, in fact, do these as charts. These are called error bars. I go to charts here, go to bar, call up error bars, put age in the vertical axis, and put gender into the horizontal axis. And this is us graphing those confidence intervals. This is what they look like side by side. Yeah. See? So notice that the male confidence intervals are slightly closer together than the female confidence intervals. We'll talk about how that happens in a moment. Okay, so now we've got these confidence intervals. What's the importance of this, and why is that useful for us? Well, in this example, the mean age happens to be 34.74. Okay, so it happens to be 34.74. Of course, we don't know what the mean age for employees is in the population that the sample was drawn from, but the confidence intervals indicate that it is likely to be contained in a range like 33.67 to 35.8. Okay, so somewhere in there, we think. And as we know, drawing another sample would probably result in a slightly different mean value. But the point is that all of our statistics are likely to vary from one sample to the next, not just the mean. So if we drew another comparable sample and recalculated the confidence intervals, they too would probably be different. In other words, we can't get too hung up on the values of the confidence intervals themselves any more than we can fixate on the precise value of the mean. What we can say, however, is that even if the intervals vary from one sample to the next, they are likely to be broad enough that on 95% of occasions, these intervals will contain the population mean, i.e. the parameter. What we cannot say is we are 95% confident that the population parameter is between X and Y. At this point, I used to go out into Google and I would type in how to correctly interpret confidence intervals. And the first hit you would get off Google would say, it would tell you that you're 95% confident that the population parameter was between X and Y effectively, which was absolutely incorrect. Nowadays, I think it's using its own AI system, generative AI, to be a bit more accurate. And we can't say that. That's because the intervals themselves will vary from sample to sample. And the reason I'm pointing it out is because it's a real schoolboy error and it's a thing that people tend to get criticized for if they put in a report. It is the procedure that on 95% of occasions will capture the population mean. So let's do that. I'm actually going to show you this. I'm going to open up a data set here. I've got a data set here. I'm going to be calculating lots of confidence intervals. I'm going to open up a data set here. There's 3 million records in this data set. Okay. And I'm going to run some syntax and I'm going to calculate the confidence intervals 20 times over. And what it's going to do is it's going to take from this sample of 3 million, it's going to repeatedly take samples of 50 cases, just 50 cases. It's going to start off, show us the average overall for a value, the average overall, and it's going to show us the confidence intervals each time. And what we should find is that on average of our 20 times we run this, that the confidence intervals 19 out of 20 times will capture that interval. So we run that. There is our population mean, 3 million, 3.33. The first confidence intervals come up. There it is, 2.51 to 4.401. So 3.33 is within that range. Next one, very close, look, 3.52, 2.24. Next one, 2.88, 4.40. So sometimes when we run this, we find that every single confidence intervals, all 20 of them. All right, there we go, right away. So there's one that failed to capture it. Usually find that on average, 1 out of the 19 will not do that because it's a 95% confidence interval. So you might find it's 2 out of 19 sometimes. Sometimes it's all 20 capture it correctly. But so far we found one thus far that hasn't captured it. All the other ones thus far are capturing. We're up to confidence interval number 9 here. We've got another 10 to go. Next one's there, 10. Okay. So what's driving this? How does it figure this out? It figures it out using something called the standard error. And the standard error is just like a standard deviation. It's a measure of variation. But instead of measuring the variation within a sample, the standard error tries to estimate how much a variation will vary from one sample to the next. So we're up to number 14 now. We've got 5 to go. Let's see if it finishes it. 5, okay, that's 3 points. So far, only one of the samples, only one of the confidence intervals that we've calculated thus far has failed to capture the mean, the overall mean of 3.33. And I got 17. We only got another 3 to go. Let's just wait until it finishes. Here's number 18 coming up. Different sample of 50 cases. Still 3.33 is captured within that. Here's number 19. Still 3.33 on number 20. Let's see if it captures it. 3.33 is within that. So 19 of our 20 confidence intervals captured the true mean value. So the technique itself will, on 95% of occasions, capture the population mean. This is exactly what we're saying about it. So the special statistic that drives this is called a standard error. And the only reason I'm mentioning this is because when you see confidence intervals which are far apart from one another, you know, if you look at one group and they're far apart from another, the thing that's driving that is the standard error of the mean. The standard error of the mean are useful for calculating confidence intervals because it's actually just the standard deviation. You can see it here, sometimes see it pop up in statistics here. It's actually the standard deviation of measures, on average, how much one sample mean would vary from one sample to the next. So it's a kind of standard deviation of one sample mean to another sample mean. And to calculate the confidence intervals, the 95% confidence intervals, what you do is you multiply that number by 1.96. For various statistical reasons, you're roughly doubling it. And you take that away from the mean and you add it to the mean. And when you take this nearly doubled number here of 0.542 away from 34.74 and add it 34.74, you get 33.678 and 35.802. Those are your confidence intervals. So it's really, the standard error itself is based on the ratio. It's calculated based on the ratio of the standard deviation and the sample size. And the reason I'm pointing that out is that therefore it is affected only by two things. One, which is the size of the sample, and the second is the spread of the data in that sample. So confidence intervals move further apart if the sample is smaller and or if the sample has more spread. And confidence intervals move closer together when you have a larger sample and or you have lesser spread. Why is that important? Well, we looked at this group here, the female group here, and we were just looking at and seeing that the males and the females, and we look at the males and they're slightly closer together for the male group here. Well, it could be that we've got a larger sample for the males, and or it could be that there's less variation in the age sample for the males. So either one of those things will drive if you've got a more standard deviation or a smaller sample size, because you can't be as confident, if you like, it pushes the means apart. Note that these two means do not overlap with each other. So it's possible that the mean actually is the same for both of these groups in the population. That's a bit like doing a significance test. It's not the same as doing a significance test. I have to say that it's not the same, but it's kind of a hint that if I did a t-test here, that we would probably find that that we didn't reject the null hypothesis that the two means are equal in the population. That's because a t-test focuses purely on the difference between the two mean groups, and it's really saying what the difference is, whereas the confidence intervals are really looking at the two means and trying to calculate how reliable your sample mean is, and that's slightly different. Note that, however, if I compare three groups, and this is why they're quite useful, you're comparing three averages. Look at the custodial group. Look how far apart their confidence intervals are. We know from we saw earlier on, the custodial group is quite a small group. So one of the things which will push the confidence intervals apart quite a lot for the custodial group is the fact that it's a smaller sample size. So you can't be as reliable. Therefore, the confidence intervals are further apart. And note also that they tend to have a higher average age of just under 50 or about 50. than clerical workers and managers, and that the confidence intervals do not overlap. We may well find that if we were to do a one-way ANOVA here, we might find that in fact this was a statistically significant difference, and we would reject the null hypothesis that the means for all three groups were equal in the population. Okay, that takes us to the end. Now, further reading for this, we have a little blog series that goes through this in a bit more detail. That kind of talks about these points, the difference between testing and inferencing, and what's standard about standard deviation. It's often finding normality. Why is the normal distribution so important? You might want to use this as follow-up reading. I would recommend the following book. This is a really good book, The Art of Statistics by David Spiegelhalter. It's a really good introduction to statistics and really deals with a lot of these problems that we're talking about and a lot of these concepts. You should bear in mind, of course, that we have our own consultancy. We can help you analyze your own data. We can teach you how to do this yourself. We can provide training and support, and we also help with the recruitment of staff into your organization. If you've already got SPSS, some of you probably may not have a SPSS, but if you already got it, we can help manage your existing SPSS licenses. And you can buy your analytical software directly from us, often with discounts. We always offer no strings attached technical and business advice related to all things analytical to all comers. So you don't have to be a customer, you just have to email us and ask us. We offer formal technical support services around the IBM SPSS product support, with ticketed support. And our customers get access to our free library, our library of training materials and recorded self-paced training courses. So there are advantages to being a customer of Smart Vision using your SPSS and having us manage your SPSS license. It's something to bear in mind. In the meantime, I hope that you find that useful, and we look forward to you logging in again in the future. You should bear in mind that we have a series of webinars that we run throughout the year, and we also have a series of recorded webinars from our previous webinars. So do look on our website to check out previous webinars if they are of interest to you. Thanks very much, and we look forward to you logging in again in the future.